All right, we're going to take a look at a couple of the practice problems on page 260 as some examples. So we want to find the Ksp, the solubility product constant for each of the following. So Ksp is really looking at when a solid dissolves, what is the equilibrium that is created by that solid dissolving. So the first thing to do with these is to go ahead and write a reaction to show the dissolving of that solid. We've done this plenty of times. It's simply breaking apart our chemical into its ions. So calcium carbonate, solid, and we're going to break it apart into its ions. So we have calcium ion with a 2+ charge. You do need to include charges, plus carbonate ion with a 2- charge, also aqueous. Okay, so this one is not very soluble. This chemical is not very soluble. That's why we have a low solubility there. But we're going to be able to find that equilibrium constant. So this value, 6.1 times 10 to the -5 molar, tells us what the molar solubility is of this. So what we can do, the easiest way to kind of set this up, is say, okay, if this is 6.1 times 10 to the -5 molar solubility, then we use that and think about our mole ratio of our chemicals and say, okay, well, if one of these dissolves, we're going to make 1 calcium and 1 carbonate. So it is an equal amount. Well, this is a molarity. This is moles per liter. We can relate them with their mole ratio. Well, if it's a 1-to-1-to-1 ratio, it's all going to be the same amount. So if the concentration of the chemical when it dissolves is going to be this, then the concentration of each ion is also going to be that number. Okay, so this is basically that equilibrium line from our ICE table. Okay, these values over here. So if we want to find our solubility product, our Ksp value, then we need to set up our equilibrium expression. For these, since we are dealing with a solid dissolving, we only need the products. That's why it's called the solubility product constant, because it's just the products of the chemical dissolving. So there is no denominator for this. Because it's a solid, we don't include it. Then, I'm just going to separate this out. We've got the value, the concentrations for each of these are 6.1 times 10 to the 5th molar. Since they're the same, I'm just going to write that number once. And we are going to square it. Actually, we don't have to include the units for our equilibrium constant. And then we can go ahead and calculate. So we have 6.1 times 10 to the -5th. And then I like to hit enter just so it's in there, and then I square that number. Now I'm going to get it into scientific notation. Enter. So 3.721 times 10 to the -9th. We've only got 2 sig figs. So 3.7 times 10 to the -9th, right, is our solubility product, our Ksp value, right? So that would be the same type of process for letter B. The only thing that's different, if we were to write this equation, this reaction, so MnOH, manganese hydroxide, a base, solid, breaking down into manganese. Hydroxide has a 1- charge, so manganese has to have 2+ to balance that charge. We get 2 hydroxide ions. Okay, so if the solubility of this chemical is 3.6 times 10 to the -5th, it would be equal for Mn2+, but twice that amount. So we multiply this by 2 for this one. We take our values and plug it into our equilibrium expression. Okay, and we'd want to square the OH because it has that coefficient of 2. So you can try that one out as an example and let me know if you have any questions. For this next part, it says our solubility of barium chromate and gives us our value. We still want to find our Ksp for this. So this is just different in terms of the solubility. It's telling us how many grams are soluble per liter instead of giving us moles per liter. So we're just going to have to do an extra step with this. And that first step is just going to be changing this into molarity. So this has our grams of our chemical per liter. All right. Well, we want to change those grams into moles of barium chromate. They didn't give us our symbol for barium chromate. Barium is Ba. Chromate, you'll find in the back of your book in your table, should be Cr04. 2 minus. I'm just going to make sure. So you can find it in the back of your book under page 570. So chromate is down here. We don't use that one. Cr04 2 minus. Don't use that often. So barium is a 2 plus. Chromate Cr04 is a 2 minus. So BaCr04 is our formula. So we need the molar mass of that. Fun. Okay. Grab a periodic table. So our mass of barium, 137.33. Chromium is 52. And then 4 oxygens, 4 times 16, gives us, give out scientific notation, 253.33 grams per mole. Now when we calculate that, those grams cancel and we're left with moles per liter, which is molarity. So we've got 2.8 times 10 to the negative 3 divided by 253.33. Be a pretty small number. So we've got 1.1 times 10 to the negative 5th molar. Okay, so we're going to then approach it the same way as we did with the previous ones. So we can take our chemical barium chromate, write its reaction, right? Since this is a 1-to-1 ratio, this molar solubility of our chemical is equal to the solubility of each of the ions. So we can go ahead and write our Ksp equation. So we know it's Ba2 plus and then Cr04 2 minus. And then we can go ahead and add our numbers in there. Again, it's going to be equal amounts because it's 1-to-1. So I'm going to go ahead and put my 1.1 times 10 to the negative 5th. Since they're the same, I'm going to go ahead and square it. And our Ksp is 1.1 times 10 to the negative 5th. And we'll square that. So we get 1.2 times 10 to the negative 10th for our Ksp value. All right, so we'd approach these questions the same way. We just have to do a little calculating, a little converting first. When you get down to the bottom, it says a student prepares a saturated solution by dissolving 5 times 10 to the negative 5th moles of magnesium hydroxide in 500 milliliters solution. Again, we have moles and liters or milliliters, so we need to find our molarity first, and then we're going to approach it the same way as number 1. Okay, so a lot of these they're just getting to that molarity first and then completing the rest of the problem. So try those out. Again, if you need help in class, let me know. All right, we're going to take a look at an example on page 263. So we want to find the solubility of each of our chemicals. So from the Ksp value. So this is going to be like on page 260, but working backwards. So instead of trying to find Ksp, we're going to have that, and we're going to try and find the solubility of our chemical. Okay, how much of it will dissolve was the concentration of that chemical. So our Ksp values are not given in the problem. They are on page 572 of our book. So I'm going to go ahead and let's look up silver chloride for part A. So we have that value. So page 572, if you go down to the bottom, silver chloride has a value of 1.8 times 10 to the negative 10th. 1.8 times 10 to the negative 10th. So it's Ksp is that value. Oops, there we go. So let's take a look at silver chloride. It's good to start with a reaction so we can see what's going on. So when this breaks apart, we get silver ion and chlorine ion if it was to dissolve. Now it's not very soluble, so we're going to get that's why we have such a small Ksp. We get very little actually dissolving. So we want to take this Ksp and figure out what the concentration and that molar solubility really is. So the way we can do that is like our ice tables, we can assign these chemicals X. So we start out with our solid, which has whatever the concentration is, that solubility, that's what we're looking for, some value of X. And when it breaks down, we're going to add these values of X here. So we get X and X of that chemical. Okay, so it's a 1-to-1 ratio for our substances here. You can see on the page 262 right next to this, they use S. You can use whatever variable you want. I like X, so we know how to solve for X. You notice in the one on page 262 that they have, for the products, the hydroxide OH ion, it has a 2 in front, so it has 2S. You would do the same thing. If this had a coefficient of 2, we'd write 2X. Same idea. So now, we want to figure out what these are. Now, I have a Ksp value, but we can create a solubility product equation or expression. And again, it always includes just your products, just your aqueous chemicals. Okay, so we don't know what these values are. They're going to be X, but we do know what the Ksp actually is. So 1.8 times 10 to the negative 10th is equal to these values. Well, these are both X, so X times X gives me X squared. So we can solve for X by taking the square root of both sides. So X is going to equal 1.8 times 10 to the negative 10th. Put that in my calculator, and then I'm going to take the square root of that number. We get 1.3 times 10 to the negative 5th. So that is our X value. That is the molar solubility of this substance. So 1.3 times 10 to the negative 5th is the basically concentration of AgCl. Its molarity. Oh, I hate when it doesn't show the whole thing. Alright, so we took the square root of this and got our X value. That X value represents our solubility of our solid. So if we saturate that solution, we're going to get 1.3 times 10 to the negative 6 molar of AgCl. That's our max we can get. Alright, so these other questions are very similar. You can look up the Ksp value in the back of the book. You can write an equation to show how it's dissolving. Use X to represent your numbers and plug those into your expression and solve for X. Okay. For these ones, go ahead and just do it in molarity, in moles per liter for these. Okay, you can leave it in moles per liter for your other questions. For number 2, what is the concentration of hydroxide in saturated solution? So this would be looking for like one of the specific ions, so whatever that happens to be. So it says a hint, write out the dissociation equation and Ksp expression first. So this is it's just like writing out this in your Ksp expression and then thinking about what you want to solve for. And then go ahead and for number 3, what mass of calcium oxide is dissolved in a 650 milliliter saturated solution? So if we go ahead and solve just like we did up here, solve for X, we're looking for grams of it, and we have the volume, and if we can solve for the molarity, so we can find moles. Right? So try those out. If you have questions, again, you can ask in class. Thanks, guys.